So hello, everyone. Welcome to the Asset Seminar. So today, our speaker is Dan Roth. Unfortunately, Dan's plans changed at the last minute, and he couldn't be here in person, but we are still glad to have him talk to us virtually. So as all of you know, Dan is a professor in computer science here, and he's a world leader in natural language processing. And in the last couple of years, he has been building a large team at AWS AI at the intersection of large language models and reasoning and code generation. And today he's going to tell us about the question that's on everyone's mind. What's next in language models? Dan,
Okay.
please go ahead. Yeah.
Can you hear me well?
Yeah.
Okay, thank you very much. Again, I really apologize that I cannot be there. This was the plan, but I had to travel in the last minute. So still happy to be here. And you know, it's clear why we are talking about all these things all the time. I think Gen AI is in the news. And if I manage to move my slides, you will see that. So everyone is talking about whether we solve it all. Is it AGI? I personally hate the term AGI. I don't think that we are any close to it. But you know, it all started to be very exciting with ChatGPT coming out just about a year and a half ago. And of course, Microsoft is using it, but there are many other companies, Google, Meta are involved, and Amazon, of course, is also playing in this field with a slightly or a very different, I guess, business model. So you hear a little bit less about it. But everyone is really excited about it. At the same time, we all hear about these problems that we have. And you all seen this, you know, for example, when ChatGPT invented the sexual harassment claim against a real law professor. And these are not just things that, you know, you can look at it in the news and say, this is unfortunate. These are all hallucinations. And these are cases where companies are going to start paying money for. This is one case that happened just very recently with an Air Canada chatbot. And very, very recently, I think about 10 days ago, very close to home, the New York City actually started a chatbot that helps people understand regulations and rules of the city. And it turns out that it's not working so well. So there are many problems, and it has to be clear that these hallucinations are not due to just reading wrong information somewhere. Typically, they are a reflection of making wrong decisions by the model, and there are many other examples of models making wrong decisions that did not make the news yet. So we have to ask the question of where are we, and it's clear that everyone is very excited about large language models and their multimodal counterparts. And I think that there are a lot of reasons to be excited about. I mean, clearly there's been a huge progress in this space, but we have to, I think, interpret the technologies more carefully. And I really think about it as a collection of new technologies that will allow us to develop better assistive technologies if we made the right decisions. And it has to be clear that if we misinterpret the technologies, we may take it the wrong way, or we may miss it. So understanding what we can and cannot do is really important, because it will allow us to deal better with the risks, limitations, and benefits of these technologies. So the first half of my talk is actually going to be really a perspective that I want to give on where we are and where we are not. And I'm going to start with a couple of disclaimers. So first of all, I'm going to use examples for multiple models. Don't take this as a criticism of specific models or companies, just part of the discussion where I want to shed light on the state of the technology. And a lot of the examples that I'm going to give today that show that models can or cannot do various things are no longer true, because these are examples that were taken, 2, 3, 4 months ago. and things are changing both directions. Things that worked before do not work today, and things that didn't work before could work today. But still, it's a pretty good reflection of where the technology is. And I'm going to start with talking for a second about the model solution gap. So one thing that Twitter tries to tell you, or people on Twitter try to tell you, is that once you have a good model, problem solved. We can solve all the world's problems. But really, this isn't the case. There's a big gap between models and solutions that people can reliably and consistently use. And I'm giving this illustration here where it's a bunch of data sets. Maybe these data sets are not the best way to evaluate qualities of models, but there's some way to do it. On the right side, you see tasks that are mostly focused on memorization related tasks. On the left side, you see tasks that are mostly decision-making or reasoning. And you can see that we are not doing well. So on average for this task, maybe we are doing kind of in the 50s for decision-making tasks, but really for decision-making tasks, we need to be close to 100%. So this is the gap that research should focus on and hopefully fill in the next few years, one way or another. To start, I want to go back about 55 years ago when Terry Winograd wrote a thesis at MIT called Shrewdlo. So what Terry did is basically developed a program that was able to communicate with humans about a real world, about Block's world, and reason about, can you move this to this place? Can you place this on that? And so on. And really a program that maintained a good conversation with users about this real world. Some people thought problem solved. We solved NLP. We can converse with models. Really, he knew, and people that thought about it more carefully knew that it wasn't the case. In his specific case, one of the problem or the key problem was that the world was very small, maybe about 50 objects. So most of the decisions were unambiguous. Was there any comment or question? I can't see you. Is there a question?
No.
Okay. So there were very few ambiguities the program had to deal with. It wasn't. Okay, I heard some echo maybe. Anyhow, so the program was quite impressive, but not what people thought at that time. Now, fast forward 55 years, models today are much better, and they can keep very good conversations. And I'm showing here the conversation that the New York Times, a tech journalist, Kevin Roth, had with a ChatGPT using Bing. This is something that actually made ChatGPT in many respects famous. And I'm zooming in so you'll see how fluent the conversation is, and how knowledgeable the model is about things. Very impressive, definitely fluent, and the question smart. I don't know about smart. I mean, at the end of this conversation, the model suggested to Kevin to leave his wife and move in with it. But it's clear that this is one of the key lessons that we've learned over the last couple of years. We learned that being linguistically coherent is much easier than we thought. You take a very deep model, train on trillions of tokens, in a very simplistic way to predict the next word, it can generate coherent text. And I think that part of the excitement is because we were trained all our life to equate being linguistically coherent with being smart. And we project this on our current conversational models. I don't think this is the case. And before we get to analyze it a little bit, I just want to focus on one point. I don't know if all of you have thought about it. What does it mean to train on trillions of tokens? An average book, let's say 200 pages, has about 100K tokens. So when we talk about a trillion of tokens, we're talking about 10 million books. Most models today are being trained on multiple of trillions of tokens. Now, this is a huge amount of text. So perhaps we are underestimating the power of memorizing so much text. We as human beings memorize nothing, basically. So we are very impressed where models can access a lot of information that we didn't think is even written anywhere. And perhaps there is some confusion between what models just know because they've read and other properties that we attribute to these models. This is something to keep in mind. So I'm going to start my discussion related to this ability to memorize and interpret this. Now, we all know that it's very difficult today to evaluate language models. We have to come up with new methodologies and new technologies to understand this. So I'm going to give a snippet of results that is relevant to it from a very recent paper that was done in my group, where the emphasis there was to develop methodologies to evaluate instruction following and hallucinations. So the game we're playing is quite simple. So you take a piece of text, a QA data set. In this case, the question is, when did Athens emerge as an economic power? And we have the context that you can see here, the evidence and the correct answer. We are perturbing this in two ways. One way at the top, which I call answer swapping, we use only questions that the model knows how to answer, both open source and open book and closed book. So, and then what we do, we replace the old answer. For example, the 6th century, we replace with another answer, maybe the 4th century. We know that this way we've generated a conflict between the parametric knowledge the model has and the context we are giving it. And we ask the model in the prompt, use the context to answer this question. The second modification we are making, which I call here at the bottom context enriching, we're taking questions that the model can answer open book. That is, if we give it the context, it answers correctly. It does not answer correctly closed book, so it doesn't have the information in its parametric knowledge, or likely doesn't have it or cannot access it. And now what we are doing, we just keep the context as is, but we augment it with additional relevant context. So we retrieve a piece of information, piece of text that is on the same topic, it's relevant. We augment it with the relevant context, and we do it in such a way that the truth value of the answer does not change. It just makes the context, the input context, a little bit more complicated. So in these two settings, we can evaluate models. And what I show you here on the left and the right, answer swapping and context switching, results of models. We compare it as gold standard, if you'd like, with Amazon trackers. We all know that this is not a real gold standard, but this is sub 10% errors. And all the models, all the top models are making 20% and more errors, and in the context enriching, even more than that. So how do we understand this? So maybe understanding language, which we require the model to do here, is much harder than generating language. Or perhaps our generation evaluation is too lenient. We sometimes think, oh, wow, this is perfect generation. It's very nice. And we don't notice a lot of things if we don't evaluate it more carefully. And I think that probably both of these are at play here. Understanding is harder, and we don't know how to evaluate well, or we are too lenient when we look at text. So with that, let me move on to what I want to focus on in the first part of the talk, and this is reasoning. Now, reasoning used to have a definition in AI. We used to know what we mean when we say reasoning in old AI, let's say. This is no longer the case. We are looking at a range of phenomena. But anyway, you want to think about it, and it really won't matter for the discussion today, is I think that all form of reasoning boil down at some point to some deduction. And we know the deduction is hard. So probably models cannot do this the way we expect them to do. But regardless of that, I'm going to give a few examples of various kinds of reasoning. And I'm going to start with an important form of reasoning that is spatial reasoning. So I'm going to zoom in so you'll see the problem. The cup is on the right of the plate, the spoon is on the left of the plate, the knife is in front of the spoon, and so on. And then I'm asking, what's the relation between the knife and the saucer? Now, if you were tasked with this, what you would do is you will read this problem and you'll take a piece of paper and you'll draw it. You'll put the spoon here, the saucer here, the cup here, and then you will look where is the knife and where is the saucer, and you'll be able to say what's the relative position. And amazingly, GPT-4 can actually solve this problem. And everyone is very impressed. Why does it solve it? My interpretation is what I call here token bias. The model has seen related cases. The model has seen many, many problems or statements where A is to the left of B, B is to the right of C, D is on top of D. What is the relative position of this? And the model can basically use this as a way to answer it in this instance. But if you try to systematically quantify the performance of models on this kind of task, and it's very easy to do it in this case, you can just take a few objects, let's call them, DG, BG, JF, develop a story of relative positions of the different objects. J is below B, B and G is side by side, and so on. And then ask a question with respect to two of them. And when you try to quantify this, you see that, for example, GPT 3.5 solves between 25 and 45% of these cases, depending on the difficulty. And that's the case for all top models today. There's been several studies of this that show models actually do this, but they do it sometimes, and in fact, very infrequently. Perhaps not surprising. Let's move to another type of reasoning task, reasoning about sets. This is really an important task. And I'm going to zoom in to this problem here. Every person in the US is taller than my sister, so I wonder if every person in Alabama is taller than my sister. You know the answer, but you can read here what's the answer of the model. And to me, the answer of the model is completely nonsense, right? So the model focuses on being politically correct. It's important to remember that height is not the only measure of a person's worth or value. And it doesn't matter whether the model says it's unlikely, as it says in this case, which is wrong, and sometimes it will say likely. Just the fact that it gives me this answer, to me, indicates the model doesn't understand what I want. What I want in this case is yes. The answer is, the problem is very simple. The answer is simply yes. And the fact that the model gives me these answers indicates to me that it doesn't really figure out the logical structure of the problem so that it can answer carefully. And this happens in many other problems. I'm going to give a couple more. This is a quantitative reasoning problem about sets, where I start by asking the model to list US presidents since 45 and the number of children they had. And this is the list. It's a pretty good list. There's a mistake here. Joe Biden is a mistake, has more than one child. But Clinton, for example, is correct, has one child. But then I'm asking a reasoning question with respect to this list. List the US president since 45 that had at least two children. And now, when I get this list, I notice Bill Clinton is here too. And we just saw in the previous list that the model knows that it had only one child. So this could be funny, but really indicates a problem that we have to think about. And all of you probably have played with quantitative reasoning. I'm not going to stop and play with this. Instead, I'm going to quantify how models are doing. And this is basically a very recent quantification of how models are doing on computations in the range 10 to the minus 5, 10 to the 5, for operations, and multiple models that you can see here. Now, of course, this is clear. It's not surprising that models do not do it. And in fact, I don't think that we want to train models to do it, but this still gives some indication of where we are in this space, if you were to believe that models can do this kind of things. More relevant is, for example, scheduling problem, where you want to ask a model to schedule a meeting between three people when the constraints are given. And models typically cannot do it. I mean, if you spend 20 seconds on this text, you will see that the only time that works is Monday morning. ChatGPT typically responds incorrectly. And what is even worse is that you can converse with the model about this, and you can lead the model to answer whatever you want. So models are really not capable of addressing these kind of questions. And if you think about how we train these models or pre-train these models, really, we train them with a very simple supervised classification task, right? So we mask something and then we use, depending on the models, two-sided context or one-sided context. This is more, this is most of the generative models today. And that's what we do. We train on predicting a token given the context. Now, this, by the way, was also the key excitement, I think, from these kind of models, because this self-supervision gave people the feeling that, wow, old machine learning is dead. We don't need to collect a lot of annotated data. We don't need to supervise model. We can rely only on self-supervision. And that's really exciting. However, we all know also that this is no longer true, right? So today, the very large models use huge amounts of supervision, both in their SFT, supervised fine-tuning, and following that in some reinforcement learning type approach, where it's a lot more expensive than old machine learning annotation because the model is in the loop, right? So you have to provide input to the model, get predictions from the model, core them somehow, and then provide feedback. So the supervision is actually much harder. But the bottom line at the end is that the way we do inference, it's basically an autoregressive model. You know, it takes a bunch of tokens in the input, outputs a token one by one. The produced model goes back to the input, and we continue this way. So it's a feed-forward network, and this kind of model have shortcomings. And the few examples that I gave before are not a random collection. There are certain difficulties that model run into in quantitative reasoning of different sorts, in aggregation of information whenever you have to develop an intermediate representation and then reason about it. Whenever you have problems that have to do with, you know, spatial data types like time and space, or whenever you have to be able to, you need to be able to backtrack, you know, look ahead, problems cannot do it. And there's been a beginning of understanding, of theoretical understanding of how should we think about it, what are the computational limitations of models, and what are the pitfalls, if you want, of the way we train models today. I'm very interested in this. If people want to talk about it, I'm not going to dive into this more, but just to say that, you know, we understand that there are limitations. Now, I'm not saying, oh, that was too fast. I'm not saying that we cannot address these problems. What I'm saying is that we cannot expect that LLMs as is on their own will be able to do it for us reliably. We have to do more than that. And of course, there's the truth, right? So models cannot tell the difference between truth and things that seem to be true. And if you really think about it, the training process inherently encourages model to hallucinate. And you can think about it multiple ways. Perhaps the simplest way is to think about the supervised fine-tuning process, where we provide input and feedback to models. For example, you can ask the model, who is the first president of the US? And then you provide an answer. Now, you don't know whether the model knows it or not. So basically, you teach the model, for some questions, just give me a name of a person. Whether you know this to be true or not doesn't matter. And there are many, many cases of this. I'm not going to go into the details of these examples here. There's another relevant paper that I can highlight here that also discusses this in the context of expert curated questions and answer that the Chaitanya John's unit with Mark Yatskar has been working on. And, you know, there are many types of hallucinations. I'm highlighting here two types just to mention that some of them we have a better chance of dealing with. For example, factual questions might be easier to deal with, or factual hallucination, than some other fundamental reasoning hallucinations. But in both cases, we'll have to go outside the model in order to handle it better than we do it today. Okay, And I want to continue with a couple other examples before the bottom line of this part. And my example here is a very important example of discussing things with my sport assistant. So this is a recap of a football game. I assume all of you in the audience understand American football perfectly well, so you can answer all these questions. And I'm going to ask my sports assistant a few questions and see what they can do. So the first question I'm going to ask is, how many touchdowns did the Eagles score in the first quarter? And I'm going to help you here by highlighting where the answer is. And it's written verbatim here, so all models will be able to answer it. The answer is 2. My next question is going to be a little bit harder. How many field goals did Washington score? And you can see here, I'm highlighting the relevant sentence. They now have 9 points. Now you can think about how did they reach 9 points? Of course, you need to have some understanding of the game. You need some resource. And the answer is 3. But if you understand football, you know that you can reach 9 in multiple ways, not only using 3 field goals. Although in this case, the answer is correct because the sentence says field goals. Once you have plurality of field goals, the correct answer is 3. Now, models answer 3, or those that answer correctly answer 3, but they don't know why. And they answer it correctly for the wrong reason. I wasn't able to get a good explanation from any model for this. And I can ask one other question. How many field goals did the Eagles score? And again, I'm highlighting at the bottom of this paragraph. Now they have 17 points. They used to have 14 points. So you note what is the answer. Models cannot answer it typically. A model would say the given news story does not mention any field goals scored by the Eagles. And it's true, the text doesn't mention, but we can make this inference just by looking at relevant information around it and understanding the rules of the game. And this is really the bottom line of what I want to say here. So the world has a symbolic structure. People often, not always, find this symbolic structure and use it to reason consistently. LLMs cannot find this symbolic structure. Sometimes the token bias, the fact that they've seen very similar things under a very complex notion of similarity, this token bias produces the same response as if they found it and everyone is happy. So the second lesson that I want to highlight is that we actually learned that often token bias, especially once you train on trillions and trillions of tokens, is actually consistent with reasoned conclusions. So, some people think about it as kind of Daniel Kahneman's think fast, think slow, system 1, system 2, whatever you want to call it. But to me, this isn't sufficient. It isn't sufficient that token bias is consistent with reasoned conclusions often, because when we make decision, we need it to be perfect. We expect our computer programs to find the structure and to be consistent all the time. Imagine what would you do if your calculator would give you the correct answer 70% of the time. I want to emphasize this point. Okay, so really the way I think about it is what we are doing here is inductive learning. Inductive learning has some probabilistic guarantees as a function of the example we've seen in the past. And that's good, and often it gives us a lot of good performance. But sometimes we need exact learning of theories. Maybe not for text generation, because the option, there are many options, and we don't notice whether we say it this way or another way. But to support some decision making, we do need exact. And this is much harder to accomplish with the current technology that we have. To push this point a little bit more, I'm going to give one more example. This is an example that hopefully many of you have seen before. This is called the Wason selection task, popularized, I think, by Johnson Laird when he talked about model-based reasoning probably 30, 40 years ago. And the task is this. You're shown 4 cards. Each one has a number on one face and a color on the other. And you're asked to determine the truth value of the following statement. If a card shows an even number on one face, then its opposite face is blue. The goal is to turn over the minimal number of cards to allow you to determine if this statement is true in this pack of cards. Now, you can spend a few seconds thinking about it. I'm not going to test you here. I've done this in some of my classes. But the bottom line is that most people are not so good at it. People like us that have been trained in this kind of thinking are pretty good at it, but still not perfect. And you know, I've done it in computer science classes. People make mistakes. But when given equivalence tests that are grounded in some familiar situation, a lot more people get it right. If, for example, I'm going to ground it in, if student scores less than 650 in quantitative GRE tests, they cannot get into a top CS program. And then I give you cards with scores on one side and programs on the other side. PhD students are going to get it much better. If I give you cards with, if a student is younger than 21, they cannot buy beer in the US. And then one side of the cards is going to be age, the other one is buy or cannot buy. Most people from the street will be able to do this much better. So again, we are kind of in the regime of think fast, just predict, just evaluate based on similar situation you've seen, versus think slow, identify the structure or the constraints and then reason consistently. Must be 100% correct. Models are thinking fast, which basically is another way of saying they are doing very sophisticated memorization rather than what we would like them to do sometimes, which is reasoning. Okay, so I'm actually not going to skip. I see that I have time, so I'm going to move into some other examples of reasoning versus memorization. So this is a recent work that was done in the context of exploring the limitations of reasoning chains. I'm going to just cite one result of this paper, which I think is very, very interesting and relevant to understanding reasoning versus memorization. The goal here was to construct a new data set for QA, question answering about entities. And the way it was constructed goes like this. So you start with an entity, and then you look in Wikipedia for relations the entities participates in. For example, Leonardo DiCaprio produced Garden of Eden and also starred in J. Edgar. And then you take, now you have a question, right? Which producer of Garden of Eden also stars in J. Edgar? Now you can focus on one of these entities and continue. You can focus on J. Edgar and then identify relation J. Edgar participated in, written Dust in Black, produced by Malpaso Productions. And now you have a deeper question. Which producer of Gardener of Eden also stars in a film that was written by Dustin Black and produced by Malpaso Productions? And you can keep on going, multiple steps, and you understand the idea. Eventually, we generate a data set of a few thousand instances. All the data comes from DBpedia. So the model knows all the factual knowledge. It was trained on Wikipedia, and we can test that it knows all the factual knowledge. So how does it do when reasoning on these chains of reasoning? And you see results for various models on various lengths of the various depths of the chain of reasoning. So one observation is that the models are not good. For almost all depths, there's a huge gap between humans and a few short GPT-4. But the more interesting observation to me is that surprisingly, the depth doesn't affect the result so much. Okay, so depth 1 is much easier than others, but then it's about the same for all models across the depth. And when you try to understand what's happening here, what we realize is that really it's not the longer chains, it's the input similarity. So we plot the accuracy as a function of entity similarity. We look at entity similarity basically by measuring the similarity between the answer and entities that appear in the question. And what we see here, surprisingly, that there is very high correlation between entity similarity and performance. So really what we should see is a flat line if the models are following the reasoning chain, because entity similarity is irrelevant. All the knowledge is known to the model. But the correlation that we see here between performance and entity similarity indicates that this is really a key issue. Models make decisions better once they've seen it before, or they've seen something similar to this before. And I'm going to give a concrete example to better convince you of this. This is one example from this data set. Which producer of Gardener of Eden also stars in film A? Film A is written by Dustin Lance Beck, produced by Company B, blah, blah, blah. Produced Thunderbolt and Lighthoof in 1974. And then the model says the producer of Gardener of Eden, who also stars in J. Edgar, is Leonardo DiCaprio. Happens to be right. Now I'm doing exactly the same question. You see, it's exactly the same question. All I change is one fact. I changed the produced by a company in 1974 to produced by another company in 1968. The models knows all the facts. The structure of the question is exactly the same. The answer is wrong. Any guesses why? Okay, either I don't hear you or you are not fans of Leonardo DiCaprio. But really the reason is that Leonardo DiCaprio coincidentally was born in 1974. So this entity similarity basically pushed the answer to be correct, of course, for the wrong reason. And this really is an indication of what we're saying about model memorize very well. They don't necessarily do consistent reasoning. So what should we do? So models on their own are not powerful enough, and they're not as powerful as we thought they are, or as some PR companies or companies that do a lot of PR try to convince us. We really need to augment models' capabilities in order to support better reasoning. And there are multiple ways of doing it, and I'm listing here a few of these. Prompting is one way, and this is perhaps the most popular way because it's the easiest way. Really, prompting to me is a way to exploit the memorization abilities of the model, which is okay because models are good at that, and we can get a few percent better. But really, the fact that prompts work or changing prompts work is just an indication that the models are not good enough. Because if you say it one way, it works. If you say the same thing another way, it doesn't work. Nevertheless, as I said, it's a good way to milk the model for a little bit more performance if you can. Post-model reasoning is another way of doing it. And this includes here consistency methods where you run model multiple times. And another method that we are also working on in my group where we try to kind of query model for intermediate variables or factors and then reason on top of it with real models that can reasoning. The two most important ways, I think, that I want to say something about, one of them is augmentations of models via agents and retrieval augmented generation. And of course, this will come with the ability to do some post-prediction inference. And better supervision via what I call incidental supervision that will facilitate this augmentation, because augmenting models via agents is not simple. By itself, it requires some abilities that we have to enhance the model with. And I want to talk about these two things a little bit and see how far I can go here. So I'm going to start with another example. Here's a question. I assume that most of you don't know how to answer this question. In Yokneam, in what month of the year is the longest day? But all of you have a plan for how to answer this question. And the plan in this case is very, very simple. All you need to know is where Yokneam is. In fact, you don't even need to know where it is. You need to know what hemisphere it is. And if once you know that it's in the northern hemisphere, you can answer the question. Of course, if I ask you it about New York State, you don't need any plan because the answer to this is written in many, many places. But the need for a plan is really important. In many cases, we don't know an answer but we have a plan, or we can develop a plan to figure out how to answer it. Here's one example that I like. Here's an image, and I'm going to ask you approximately when and where this image was taken. Some of you will know it off the top of your head. Most of you will not, but all of you will be able to look more carefully at this image, read the signs, and do some search in order to figure out approximately when and approximately where this image was taken. And this happens all the time. If you want to deal with a shopping assistant and ask them for a charger for your phone, the shopping assistants have to make plans because they need to figure out, do I know which phone you have? Am I sure that I know which phone you have? Maybe you bought it somewhere else, or the last phone you bought somewhere else. How do I access your purchases? What should I ask you in order to figure out what you have? So in all these situations, doing some planning is essential. And of course, this is essential in many, many other situations. I'm going to run here quickly through an example that requires some temporal planning and spatial planning. Will we make it to the movie? Just a simple temporal kind of Google Maps like of question, but I can make it more complicated. Will we make it to dinner before the movie? And this already requires you to do a lot of things. You need to do some temporal reasoning, but you need also to know what is the duration of dinner, and you need to know this because this will determine whether you can go to a fancy Japanese dinner or maybe just Chipotle. And you need to think about parking. It's not mentioned in the question, but maybe this will determine which restaurant you can go to, and so on and so forth. And we can make this as complex as we want, but the bottom line is that even though the overall question is a relatively simple temporal reasoning question, you have to be able to do some planning, potentially backtracking, and you'll have to be able to call external models in order to support it. And models are very, very bad at it. I'm showing here on the right side a caricature of an attempt to do something like this. I think this is a Google model. Models don't know how to do it. They don't know which questions to ask you and how to develop a plan. So how do we do it? How do we augment models with the ability to plan, interact, and ground themselves with external worlds and reason, and also reason about external worlds? So this is actually the only slide I have about some work in AWS. All the rest is stuff that happens in my group, but this is actually an effort that we started, in fact, the minute I joined AWS, developing a framework that basically assumes that LLM will be the new UX, the new UI. I mean, really, this is where the disruption is going to come, with the ability to facilitate conversations with any software system. So we developed a framework that we called Dialogues to API, basically the idea that we need to converse with many APIs. And this is still, and this, by the way, came out before ChatGPT. Only after ChatGPT came out, people kind of started to believe that this is a good direction, but that's another story. So the ability to interact with all software systems will allow us to facilitate quantitative, temporal, spatial reasoning, and many, many other things. But in order to facilitate this, we still need to have some abilities to do reasoning, to do the composition of queries, to do some planning. So now you can blame me for cyclic thinking. On one hand, I'm saying, well, models cannot do it. On the other hand, I say, even to augment models and go out to use tools, plugins, whatever you want to call it, you still need to be able to decompose instructions, to support some minimal planning, and to reason a little bit. And I think that's right. There is some cyclic thinking here, right? So, and the solution to the puzzle, the way I think about it, is that some learning problems are easier than others. And it all depends on curating carefully data and supervision that is more careful than what we are doing today. So just to give an extreme example of why I think this is the right direction, think about trying to train a model to correctly perform log multiplications and even generalize across the length of the sequence. Versus, this is very hard. It's hopeless. And of course, there's no need to even try to do it. But think about the complexity of this versus trying to teach a model to generate a small piece of code that calls a calculator with the multiplication operation. That's much easier, and that we can do reliably and consistently. And that's where I think we should do it. Now, as I said, still, in order to do it, we have to do something. And I call this something learning to reason. The key problem here is how to identify the structure of the problem. What are the variables to reason about? And I'm going to give a few examples of what we do here. This is one of my favorite examples in this space. Everyone has seen it before. I assume that you know this guy. This is Aristotle. And the question that we can ask about him, given that, he's done a lot in the logical space, is, did Aristotle have a laptop? Those that haven't seen it before will still laugh about it because it's kind of a funny question, easy question for all of us. In fact, easy question even for models today, because 2 or 3 years ago, we developed a data set that is called Strategy QA that has a lot of such questions. And now ChatGPT and the strong models answer these data sets, probably now it's kind of 80% correct. Not enough, but still pretty good. But still the question is valid. What are the variables one has to reason about in order to answer a question like this? And I bet that if I ask you about it, all of you will pretty much give me the same answer. You need to know approximately when did Aristotle die. You need to know approximately when was the laptop invented, and you need to know which event happened first. But how do we do this systematically? How do we supervise this for this sparse event? And the idea that I'm going to give from a paper that is now a year and a half ago is how should we train model to better decompose? Really, decomposing is about finding the variables or the propositions, in fact, that support the reasoning process. And models don't know how to do it, mostly because of reasoning bias. So if I see a statement somewhere and it says the Albany in New York is more crowded than the Albany in Georgia, you know that the reason for this is that the Albany in New York has more people and less space. So the why and because is something that you know, but it's not written in the same text because people know it. So can I enrich model with this kind of supervision so that along multiple dimensions, this is one dimension that you can think about. The Aristotle example was a temporal dimension, that model can actually figure it out. When they see a claim, they know, oh, what I need to think about in this case is how many people are there and how much space there is. So really the way I think about this is about providing reasons. And we need to equip model with doing it. So one of the efforts that we've done in this space is curating a large data set, automatically curating a large data set from comparable news articles that describe the same thing from different angles. So if I look at the example here that I point to, the third from the top, these are statements about gophers. On the left side, you see that gophers hide in holes and tunnels. And on the right side, you see that gophers are capable of digging holes much larger than themselves. So if I train a model with input, the green input and the yellow output to predict the yellow output, then I kind of train a model to know that in order to hide in holes, you have to be able to be in holes that are larger than yourself. So, we've developed this technology. This is what I call incidental supervision, or this is one form of incidental supervision, because unlike standard supervision, we don't annotate for it, but we also don't assume that it is exhaustive. Sometimes it's not helpful, sometimes it is, but it's kind of like looking around yourself and seeing observations and using them for the right thing. And as I show here, these insights and the data generated can be used to train models in a better way. Many other aspects of this. I'm showing here a cool example from Common Sense. This is a very recent paper, and you can see this is visual common sense, where we ask model to generate images of a bear eating salmon on the left and a person eating salmon. And you can see it on the left that models don't have common sense. I don't know how to solve this problem, but we've done a lot of work on related problems in the temporal domain, where we supervise models to enrich with enriched data, and this can be used to force models to attend to signals that otherwise they would be missed in the standard way of training. I'm not going to give details on this now because I'm almost done, and I want to say one more thing. Again, going back to the memorization or token bias versus reasoning. So what I'm showing here are two examples where word association actually match the pre-trained distribution. I'm asking the following question. Was Gandhi absent from the 1947 Indian Independence Day celebration? The answer is yes. The model knows the answer, answers correctly. I'm asking a similar question. Was Marie Curie absent from the 1903 Nobel Prize ceremony? The model knows the fact, and the model answers correctly. Now notice that these are different dimensions. The top one is about not being in a different place at the same time. The bottom one is she was absent because females were not allowed to be in a Nobel Prize ceremony at that time. The model has the facts. You know, all these names are famous, and they are famous in the context in which the question is asked. But then I can ask the same question with different names. Was Bruce Lee absent from the 1964 University of Washington graduation ceremony? Again, I know that the model knows all the facts, but the model answers incorrectly. And again, the reason is that the entities are rare, or the combination is rare, and the model is not able to kind of retrieve this using its sophisticated similarity function and get it right. So what should we do here? So the proposal we have is still in the domain of kind of enriching models with better supervision. The question is, can we transfer what LLMs do well to a symbolic process, which then we can apply to solve what LLMs cannot do well on? And of course, going back to what I've claimed before, we need to do it to a symbolic process because this is the only way to guarantee consistent reasoning. So the methodology we developed here is again that of incidental supervision. We generate simple examples based on problems the models can do well on, and we abstract this. I'm going to show how, and we do some divide and conquer, two types of problems, and then we use a separate model to learn Python code that solves these problems. This is typically very short Python code, an easy enough problem, and we can train a model to do this reliably. Once we have this, we can train the base LLM on pairs, simple problem, Python code, and they will do better on these reasoning problems. So just to exemplify what I'm talking about, this is the problem. Was Bruce Lee absent from the 64 University of Washington graduation ceremony? I'm going to abstract it to was person A absent from event B? And then I can find many instances of this type with the same abstract representation. Gandhi is one of them. Barack Obama, was he absent from the 1961 inauguration ceremony? These are actually problems that the model answers correctly. So I can use it to train Python code. Each one of them is a different Python code because these are different reasons. Obama was just born that year. In fact, was not born yet during this ceremony. Gandhi was absent for other reasons. So I can develop this Python code. And once I have this, and this is done completely automatically, by the way, there is some noise, of course, in the process. That's why I call it incidental. But still, large fraction of this is correct, and it's sufficient to generate a large data set that can be of pairs, question program that can be used to train a model. So how should we think about this? I actually don't know what is the best way to think about it. You can think about it, well, I'm teaching the model to solve the easy problems in the right way. And hopefully, because it's the right way, it will solve in the right way more harder problems. Or, which is my current favorite explanation, is basically we are exploiting the model's memorization ability to memorize, rather than the tokens, actually the reasoning path. And there's a lot more work to do here to really understand what's happening and how to do this the right way. But this is the way, I think, to basically to allow models to reason beyond kind of their core capabilities that they don't really have. Okay, and by the way, this is not going to be enough. I mean, we will need to extend this framework to multi-agent scenarios, develop agents that can coordinate and collaborate, because just individual agents are not going to be sufficient. There's a lot of work for us to do in this space, so it won't be boring. Okay, I was going to talk a little bit about reg, but I'm going to skip it because it's time, and I'm going to summarize. So LLMs are making big waves, and I think it's for the right reasons. There's a lot of stuff that is good and can be used, but at the same time, we need to understand the limitations, figure out how to build reliable and consistent assistive technologies, and also how to restrain it. I didn't talk about these aspects, but clearly this is also important. I try to abstract two lessons that I think a lot of people miss. My lesson one was that we are linguistically coherent. It's easier than we thought, but, and there's a big but here. And the lesson two is that quite often, more often than we thought, token bias is consistent with reasoned conclusions, and that misleads us a little bit in interpreting what models are capable of doing. I focused on reasoning, orchestration, not so much on retrieval, which is another very important and interesting aspect. There's a lot of stuff for us to do to make these models useful. Thank you.
Thank you, Dan. Does anyone have questions? Someone has to ask him a question that he doesn't know the correct answer to.
As long as you have feedback also.
Hi, Dan. This is Ting from Chris's group. Thank you for the wonderful talk. And I'm wondering if I can ask a question about the first part of the talk, where you show interesting examples when the parametric knowledge of a model conflicts with the contextual knowledge. I'm wondering if you have thoughts on what is the desired behavior in this scenario? Is it always desired for the model to follow the contextual knowledge? For example, even if a user is like malicious or tries to inject wrong knowledge to the model, should the model kind of decide when to reject this contextual knowledge and when to follow it?
In this case, I think it's completely clear. The instructions to the model were use this context to answer the question. So the model should use the context to answer the question. This is a very realistic situation. It's not kind of just a game, because, for example, a lot of stuff changes with time. If I ask you, who is the recent winner of the Australian Open? You cannot answer me based on what is in your parametric knowledge. You have to use the context that I'm giving you. And you know, for companies, this is really important. Things are changing with time. So basically, this example measures the ability of the model to follow instructions. So I definitely wanted to follow instruction in this case.
Any other questions?
Hi, thanks for the great talk. I have a question about the planning good ways to answer questions. Specifically, did Aristotle have a laptop example? I guess if we're trying to use examples like this of how you can think like, oh, he was dead before they were invented, and then using that sort of augmentation in order to train models to go through that kind of reasoning steps. I mean, this seems to make sense, although it seems like there's a really large amount of like not shown thinking there, that you should choose strategy of, did the person die before the thing was invented? Because different strategies of plan.
I can't hear you anymore.
Off the microphone. Oh, okay. So I guess I was wondering if you have an idea of how we might be able to expose the search process of how you find the kind of plans to execute.
Yeah, I think this is really a key question here. I can put a plug for another paper that we have that I think will be also in NACL this year, that looks at various dimensions that model need to attend to. Because when I ask you about Aristotle, okay, you figured out quickly that it's about time, but I can ask you about many other dimensions. Models should be able to have seen examples that allow them to explore the many dimensions that exist. It's not that many, by the way. And once they've seen enough examples, they can entertain which dimensions are relevant. And in order to do this, they'll probably have to go and search in order to see which dimensions are satisfied by the facts. But yeah, I think thinking about it as a planning problem is a good direction. Thinking about sort of evaluating all the decomposition method that we and other researchers have developed at that level is also important, because typically we are finding the easy ways and we are evaluating end to end. We don't know whether the models actually understand all the dimensions, or sometimes they answer correctly for the wrong reasons. So there's several interesting questions here.
That makes sense. Thank you.
Okay, so yeah, one last question.
Just to extend on that previous, I knew a Greek guy named Aristotle, actually called himself Aris. So there seems to be a lot of implied contextual knowledge here that we're referring to Aristotle, the philosopher, as opposed to, you know, this Greek guy named Aristotle. And so you have a large superset here in the reasoning that we seem to be ignoring.
You cut off, so I don't know if you asked the question.
Yeah.
So I completely agree. But by the way, I used to give this example similar to what you've just said. Yeah, I know someone in my son's school that is called Aris. But yes, I think you're completely right. And this is why in many contexts, the only way to do this well is to facilitate the model asking clarification questions. In cases where the questions are ambiguous or the model is not confident enough. In the planning example that I ran through, you know, will we make it to the movie, to dinner before the movie? There's a lot of clarification questions you have to ask. And in the Aristotle, you can guess this is the most famous Aristotle, but you can also ask a question, which one do you refer to? But you have to identify, you as the model have to identify where the ambiguities are in order to ask the right questions.
Okay, yeah, thank you, Dan. And yeah, thank you again.
Okay, thanks everyone.